Logical operators work on Boolean truth values. 0 equals false, any non-zero equals true. Exclamation mark not flips the truth. Not 0 becomes 1, not non-zero becomes 0. Double ampersand and returns true only if both operands are true. Truth table for and false gives false. False and true gives false, true and false gives false, true and true gives true. Double vertical bar or returns true if any operand is true. Truth table for OR, false or false gives false. False or true gives true, true or false gives true, true or true gives true. Evaluation follows left to right order. Each operand is first converted to 0 or 1, false or true, before the logical rule is applied. Real-world analogy, think of two switches controlling a light. AND is like a circuit that needs both switches on, or needs at least one switch on and not flips a switch. In C, any non-zero integer counts as true, so if 5 and minus 2 is true because both are non-zero. Bitwise operators treat the operands as a sequence of binary digits bits and manipulate each bit independently. Ampersand and, each result bit is 1 only if both corresponding bits are 1. Pipe or, each result bit is 1 if either corresponding bit is 1. Caret XOR, each result bit is 1 if the two bits differ. Tilde not flips every bit 1's complement. Double less than left shift moves bits left, inserting zeros on the right, equivalent to multiplying by 2 to the k for unsigned numbers. Double greater than right shift moves bits right. For unsigned, zeros enter on the left, division by 2 to the k for signed, implementation defined, arithmetic versus logical shift. Truth tables for a single bit A and B. When A is 0 and B is 0, A and B is 0, A or B is 0, AZOR B is 0. When A is 0 and B is 1, A and B is 0, A or B is 1, AZOR B is 1. When A is 1 and B is 0, A and B is 0, A or B is 1, AZOR B is 1. When A is 1 and B is 1, A and B is 1, A or B is 1, AZOR B is 0. For tilde, flip 0 to 1 and 1 to 0. Example, 0B101100 and 0B11000101 equals 0B10000100. Shift example, 0B00001_01110 left shift 2 yields 0B010110. Binary 22 becomes 88, that is 22 times 4. C defines a strict order that decides which operator is applied first. Precedence high to low relevant part. Tilde bitwise not unary exclamation plus minus right to left. Left shift right shift. Ampersand bitwise and. Caret bitwise ZOR. Vertical bar bitwise ORs. Double ampersand logical and. Double vertical bar logical ORs. Associativity tells how operators of the same precedence are grouped. Left shift and right shift are left to right. Ampersand caret vertical bar are left to right. Double ampersand and double vertical bar are left to right. Because logical operators have lower precedence than bitwise ones, the expression a ampersand b double ampersand c is parsed as a ampersand b double ampersand c, not a ampersand open parenthesis b double ampersand c close parenthesis. Use parentheses to override the default order. Analogy, think of a cooking recipe where chopping, high precedence, must happen before mixing, lower precedence. If you forget parentheses, you might mix ingredients before they are prepared. A common pitfall, if flag ampersand 0x0 1 equal to 0 is parsed as if flag ampersand open parenthesis 0x0 1 equal to 0 close parenthesis, because equal equal has higher precedence than ampersand. The correct test is if open parenthesis flag ampersand 0x0 1 close parenthesis equal to 0. Short circuit means that C may stop evaluating an expression as soon as the final result is known. And if the left operand is false 0, the right side is never evaluated because the whole expression cannot become true. Or if the left operand is true non-zero, the right side is skipped because the whole expression is already true. Impact on side effects functions plus minus assignments. Int I equals 0. If I plus and print open quote high close quote then left brace ellipsis right brace. I becomes 1, print never runs because I plus evaluated to 0 false. Int j equals 0. If j plus or print open quote hello close quote then left brace ellipsis right brace. J becomes 1, printf is not executed because J++ was true non-zero. This property is useful for guarding operations. If PTR not equal null and dereferenced PTR equal, to a then left brace ellipsis right brace. Dereferenced PTR is accessed only when PTR is not null, preventing a crash. Remember, if you rely on a side effect, you must ensure the left operand does not short-circuit it. Analogy: a security checkpoint, where you only go through the second gate if you pass the first one. Both and or are left to right, so the leftmost operand is always evaluated first. Explanation: bitwise tricks turn arithmetic into simple shifts or masks, which are often faster and expressive. Multiply or divide by powers of 2. X left shift n is approximately x times 2 to the n, works for unsigned and signed as long as no overflow. X right shift n is approximately x divided by 2 to the n, unsigned logical shift, signed arithmetic shift keeps sign. Example: int 10 equals 5 left shift 1, 5 times 2 equals 10. Check odd or even. X bitwise and 1 yields the least significant bit. If x bitwise and 1 equals 0, then even, otherwise odd. Example: if number bitwise and 1, print odd. Swap two integers without a temporary variable XOR swap. A XOR equals b. A equals a XOR b. B XOR equals a. B equals b XOR a, which becomes a. A XOR equals b. A equals a XOR b, which becomes b. Works only when a and b refer to distinct memory locations. Absolute value of signed integer using sign bit 2's complement. Int mask equals x right shift size of int multiplied by char bit minus 1, all 0 for positive, all 1 for negative. Int abs underscore x equals open parenthesis x plus mask close parenthesis XOR mask, equivalent to x less than 0 question mark negative x colon x. Real world analogy: shifting bits is like moving a row of houses left or right on a street. Each shift doubles or halves the distance from the city center. Masking is the act of forcing certain bits to known values while leaving others unchanged. Clear force to 0 is x and not mask. Example: clear bit 3 counting from 0, mask equals 1 left shift 3, x and equals not mask. Set force to 1 is x or mask. Example: set bits 0 and 2, mask equals 1 left shift 0 or 1 left shift 2, x or equals mask. Toggle invert is x XOR mask. Example: flip bit 5, mask equals 1 left shift 5, x XOR equals mask. Extract is x and mask then optionally shift right. Example: get bits 4 to 7, mask equals hexadecimal f0, x and mask shifted right 4. Practical scenario: 8-bit flag register where each bit means a permission. Define red as 1 left shift 0, define right as 1 left shift 1, define exec as 1 left shift 2. Unsigned char perms equals 0. Perms or equals red or right grant read and write. Perms and not exec ensure execute is off. If perms and right, test write permission. Shifts left shift, right shift are used to position the mask correctly. The combination of shift and logical operator lets you address any bit in a 32 or 64-bit word. Analogy: imagine a row of light switches bits. Or turns selected switches on and not turns them off. XOR flips their current state, and shifting moves the switch you want to control to the correct position. These operations are foundational for low-level programming, device drivers, and embedded systems. The two pairs look similar, but their purpose and the type of data they work on are different. Logical and or double ampersand double vertical bar. Operate on Boolean truth values 0 or non-zero. Used mainly in if while for conditions. Short circuit so the right operand may never be evaluated. Result is either 0 or 1. Example: if a greater than 0 and b greater than 0, both comparisons must be true. Bitwise and or ampersand vertical bar. Operate on each individual bit of integer operands. No short circuit, both sides are always evaluated. Result is another integer whose bits are the combination of the operands. Frequently used for masks flag handling low-level I/O. Example: mask equals status ampersand 0x0f, keep only the lower 4 bits. Common mistake: writing if flags ampersand flag ready, thinking ampersand behaves like double ampersand. It works because any non-zero result is considered true, but the intent is to test a particular bit, not a Boolean expression. Conversely, if a double ampersand b ampersand 0x0, one may be confusing, because double ampersand binds tighter than ampersand. In short, use double ampersand double vertical bar when you care about truth of whole expressions. Use ampersand vertical bar when you need to manipulate bits. Analogy: logical operators are like checking if whole doors are open or closed. Bitwise operators are like looking at each window of a building and deciding which are open. Parentheses and precedence. The ampersand and left shift operators have higher precedence than logical and illogical, or the expression is parsed as a bitwise and B or C++ and a left shift 1 and not B XOR 9. Compute a bitwise and B. 0101 and 1100 equals 0100, which is decimal 4, a non-zero value, therefore true. Short circuit logical, or the left side is true, so the right side C++ and a left shift 1 is not evaluated. Consequently, C stays 0, no increment occurs. Result of the first logical OR is true, which in C is the value 1. Compute B XOR 9. B equals 12, binary 1100, 9 equals 1001. Their XOR yields 0101, which is decimal 5, a non-zero value. Apply logical not 5 yields 0, which represents false. Final logical and true and false results in false, which is 0. Final values, result equals 0, C equals 0, unchanged because the increment was skipped. Explanation of side effects. The post-increment C++ never occurs because of short-circuiting of logical, or the left shift 1 also never runs for the same reason. The only operations that actually execute are a bitwise and B XOR 9, and the logical NOT. Apply operator precedence to insert parentheses. Evaluate left to right, remembering short-circuit rules for logical and illogical OR. Track any side effects such as increment operators or function calls that may be skipped. Convert numbers to binary if it helps visualize bitwise results.